This medical box was supposed to withstand high-temperature sterilization, but it was ruined after a single use. This tool housing was meant to be tough and durable, yet it cracked the moment it was assembled. They were both made from polypropylene, or PP, a plastic known for its blend of toughness and cost-effectiveness. So, what went wrong? The problem wasn't the material. It was the design. Hello everyone, I'm Blanca. Today, I'm going to talk about 3 design key considerations in PP injection molding that are often overlooked and how you can avoid issues from the very beginning. The first and most fundamental mistake, not knowing how to choose the right PP material for your product. Many designers stop at knowing that PP can be hard or soft, that is, homopolymer and copolymer. But that's not nearly enough. Professional material selection is a systematic decision based on performance, processing, and cost. Let's look at a real-world case. A client designed a medical box that required steam sterilization and chose a standard homopolymer PP for its rigidity. The result? Under 120-degree steam, the box deformed severely. Why? Because they overlooked environmental resistance. While standard homopolymer PP is heat-resistant, its dimensional stability drops sharply in high-temperature, high-humidity environments. Random copolymer PP, however, has inherently better resistance to high-temperature creep due to its unique molecular structure. Simply switching to a different type of PP solved this critical failure. Let's look at another example from the automotive industry. A snap-fit clip made from glass fiber reinforced PP kept breaking during assembly. The reason is that standard short glass fibers, while adding rigidity, make the part too brittle for a snap fit that needs to withstand impact stress. The solution was to switch to long fiber thermoplastic PP, LFT-PP. Long glass fibers create a skeletal network inside the material, much like rebar in concrete. This dramatically increases the material's impact strength and toughness, raising the assembly pass rate for the clip from 23% to 100%. So, the professional selection logic is this. First, define the PP type based on core mechanical requirements. Will your part endure bending fatigue or impact? Next, evaluate environmental factors. Does it need to resist high temperatures or chemical corrosion? Finally, make the final decision by factoring in cost-effectiveness. This is a scientific decision-making framework, not a choice based on guesswork. The second mistake, ignoring the culprit behind stress concentration. Why do parts break? In 90% of cases, it's not because the material is weak, but because stress hasn't been managed correctly. And the biggest enemy of stress is the sharp corner. Physics tells us that sharp corners cause stress to concentrate exponentially. It's like trying to pop a balloon with a needle. It breaks with the slightest touch. A tiny change that can increase a part's lifespan by dozens of times is the use of radii or fillets. Remember this golden rule: the radius of an internal corner should be at least 50% of the part's wall thickness. When this ratio is 0.5 or greater, the stress concentration factor drops by more than half. We once had an electrical snap fit with a 0.1 mm radius at its base that failed after less than 200 cycles. When we increased it to 0.6 mm, its lifespan jumped to over 10,000 cycles. In addition to fillets, for critical features like screw bosses, we also use gussets to further distribute the stress. These geometric optimizations are how you crack-proof your part from the start. It's far more effective than simply choosing a more expensive material. The third mistake, blindly increasing wall thickness for strength. Our intuition tells us that to make a part stronger, we should make it thicker. But in PP injection molding, this is often the beginning of a disaster. PP is a semi-crystalline plastic with a relatively high shrinkage rate. When you design a very thick section, its surface cools and solidifies first, while the inside remains molten. As the interior slowly cools and shrinks, it pulls the solidified outer layer inward, eventually causing, that's right, a sink mark. This is the most common surface defect in PP products. The correct engineering mindset is, use structure instead of thickness. Instead of a 4 mm thick wall, use a uniform 2 mm wall and add ribs to provide the necessary rigidity. And remember the design rule for ribs: their thickness should never exceed 60% of the main wall they're attached to. This not only eliminates sink marks but also reduces weight, saves material, and significantly shortens the production cycle. It's a win-win-win. Master these 3 points, and your PP part design will already be on the right track. Of course, real-world design is far more complex than this. If you want to dive deeper into the professional knowledge and technical details of PP injection molding design, feel free to visit our website, where more in-depth articles and guides are waiting for you. I'm Blanca, thanks for watching, and I'll see you next time.